The SNES is a very fancy pile of sand. There is no code or logic in it. Well, there's a small amount of boot code in the SPC 700, which is basically its own little computer, but the main machine has nothing. No BIOS, no kernel, just metal. So this means when the machine is turned on, we have to bring it up. This is the opposite of most other machines. For example, the Game Boy has its own boot ROM, and the Commodore 64 has a complete kernel. It is not unique, however. The NES and Atari VCS also have nothing. For this, we have to take a deep look at the 65816. Its dual personalities make it rather unique. The 65816 was basically commissioned by Apple to bring the Apple II line up to date by making it 16 bits. For this reason, the 65816 had to support the 6502 and do its best to support the N6502, not the 65C02. For some reason, it was decided it would boot into 6502 mode. This makes sense in that the 6502 code would not know how to switch out of 6502 mode, and hence it would be compatible still. However, it is not pin compatible with the 6502, so I don't see how this case would arise. Perhaps Apple decided to reset into Apple II mode and later abandoned it. Having two modes gives the machine some odd properties, such as two sets of vectors. The 6502 ones that now start at FFF4 technically, and the new 65816 ones that start at FFE4. Some of these don't make sense, as the 6502 mode will never get the break interrupt. It still uses IRQ. Technically, the COP should never happen to 6502, but I believe it does work. The 65816 reset vector will never trigger, as when the chip is reset it will drop to 6502 mode. So these are free for you to use as you please if you like. Also, abort will never trigger on a SNES. So what happens when reset interrupt fires? The DP is set to 0, data bank and program bank are also set to 0, stack high is set to 1 as per the 6502 stack, however stack low either as it was or, in the initial reset case, as the solar flare commands. X high and Y high are 0, but the lows are again as the solar flare commands. All of A is as the solar flare commands. The status registers will be in 6502 mode, and negative overflow and 0 flag will be as the solar flare commands. M and X will be 1 to ensure 8-bit A and indexes as per 6502. The BCD flag will be 0, always, unlike the mostly on the 6502. I will be 1 and E will be 1 to ensure 6502 mode. Vector will be pulled from 00FFFC. Don't worry too much about the setup here, it's just for the context and to provide a complete picture. I will be discussing it and giving more complete setup in the next video. Now that we are in our own code, first things first, we want to get into 65816 mode. This is done with a CLC followed by an XCE to move the C flag into the shadowed E flag. This pulls it low. Status flags with the exception of D are active low. Now as this is 2021 and you are not making actual cards anymore, so don't have to pay the extra 50 cents, you want to enter the fast ROM area. So we set the fast flag and then JML to the next address, but in bank 80. This is moved the program bank, but not the data bank. That is still in the 00 and thus slow. But to set the banks, we need the stack. So we set up the stack. Now we can put the stack anywhere. I recommend putting it at 1FFF as you have to break the data flow because of the registers in the shared RAM anyway. In this way you have unbroken RAM below it and then long access above it. The 65XX stack grows down memory. Load X with 1FFF and TXS. Now we have a valid known stack. Push the program bank and pull it into the data bank to set it as fast as well. Now I want to set the DP to 0 to be sure. While it will be 0 on a true reset, we don't know how the user has booted their machine. Could be from an SD card. We also may have done a software reset. So now the CPU is in a known state. Time to set up the rest of the hardware. The PPU has recommended initial setup values, which are listed in Chapter 26 of the Super Nintendo Development Manual Book 1, which I won't show here for obvious reasons. However, first we want to clear our WRAM. But why bother? If you've used a high-level language, you will know the pain of works in debug, but fails in release. Same principle. Your emulator clears it with 0. You use some value, maybe accidentally read a 16-bit value, and the high is 0, so nothing bad happens. But on an actual machine, that memory location is now as the solar flare decreed, and your code crashes. Or they reset at just the wrong moment, and now it's invalid and you crash. Or you test on your flash card and it's the third item, and it just so happens to put the right value in memory location, and your code works. Then somebody else runs it on another card, or it's item 50, and you crash. Why do it first? We need it to hold important things, such as our stack and our register mirrors. So before we do anything else, we need to clear WRAM. However, first, we'll make 100% sure we are in forced blank. This is fairly straightforward DMA, fixed source 1 byte to WRAM port. I have a 0 word somewhere, they are easily defined generally. Here, rather than drop to 8-bit to write the byte, I just write a word because I'm going to fix up the next byte with a write again anyway. I.e., if you write the wrong thing and then write the right thing later, doesn't matter it was wrong. No. Again, I have to write 3 bytes. Just overlap the write. At this point, I've wasted 2 clocks. But to do the 8 bits, 2 and then back to 16 bits would have been 4 clocks. So I'm 2 ahead still. We set the length to 0. This is because the DMA engine decks then checks for 0. So we'll stop on 0. If we start at 0, it will deck to FFFF, then check. So this way we will do all 64K via the DMA. Since the count will be 0, the source is fixed and the port has incremented to the next bank, we can just fire it again and do the upper 64K. You may be tempted to put this into a function. It seems like a nice thing to put in a function. It is not. Stack doesn't live in some ethereal plane. It lives in work RAM. So you'll JSR to it, which saves the return address on the stack. Then you nuke the stack with 0 with the DMA. Then you'll return to 0, which will hold 0, so it will break. It will RTI, then break, then RTI, and break, and so on. Not great. Now we can get on with the knitting machine, which could now be placed in a function if you prefer. But before we get to setting them, a couple of points about how the registers work and are laid out. Very few registers are read and write. They are ordered write only, then read only. So the PPU registers from 2100 to 2133 are write only. This means if you try and do an LDA 2100, it will mostly read the last thing that was on the bus, so 21, not the actual value. 2134 to 213F are read only. If you try and write to them, nothing will happen. Only this splits the VRAM, CGRAM, and OAM write and read registers. To write to VRAM, you use 2118, and to read, you use 2139. The 4 APU ports are read and write. The WRAM port at 2180 is, however, read-write, but the address setup 81, 2, and 3 are write only. The CPU on-chip registers, not to be confused with the AXY etc., are also split with 4200 to 4200D being write only and 42010 to 42001F being read only. 4016 is read and write, 4017 is read only. The DMA engine registers are all read-write registers. Now, we can't initialize the read-only registers, so we only need to worry about the write-only registers. The read-write nature is inconvenient. For example, say you want to enable sprites. You don't want to modify the other screen setup, just turn on sprites. Easy enough, we just need to set the 4th bit of 212C. So you load 212C, or the bit, you store it back. Can you see what is wrong with this code? 212C is write-only, so when we read it, we will mostly get 21 into A, or 10 with it, and thus store 31 into control. So we will turn on BG1 and sprites, and turn off 2, 3, and 4 if they exist. Not what you want, but as you can imagine, when you start out, you probably only have BG1 on, and when you turn on sprites, so the code will appear to work just fine, only to fail horribly later when you add a HUD on BG3 and spend hours head scratching as to why it used to work no longer works. To avoid this, you create RAM mirrors of the registers you need. This way you keep a copy of its last value. This also helps with setting, as you can modify the PPU registers at any time, which is not always what you want. Enabling a screen mid-frame will probably cause an ugly glitch. So you modify the RAM mirror, and then copy the mirrors into the actual registers in the NMI. How many and how often you copy depends heavily on your use cases, so you might make a dirty flag, which is checked and then if dirty does the update. You may also break it down into multiple dirty flags. For example, you probably don't change the screen mode and the base addresses every frame, so you make a flag to set them when dirty. But setting the H and V scroll registers is probably something you do often enough to just do it every time, regardless as setting and testing flags will cost you more time. There is no need to mirror all of them either. For example, OM address and data write, you will just set these directly every time you want to use them. Windows depends. Typically you get updated in HDMA runs, but if you do have some full height window effects, might be worth it. Mode 7 registers, are you doing mode 7? Yes, 100% mirror. No, don't bother. The CPU write-only registers are either set and forget or things you will fully set up and change when needed, so no need to mirror them, except 4200, which can be nice to have mirrored. The DMA ports, no need. What does this look like in code? First thing, 16-bit mode. Most registers are going to be 0, so why waste time and bytes doing it byte by byte? Also, I still have the write mirror code here, commented. This is so you can see what I would have had a mirror for. Most of it doesn't need to be written, as the clear of WRAM cleared them as well. So only values other than 0 need to be written. First up we have initial display. I'm using no caches full SNES naming for these. Best to set it blanking, as we have a lot more setup to do, and set brightness to full so when you turn it on later you will actually see something without making that simple mistake. And we clear object select and base at the same time. You might be tempted to optimize this and put your initial values into it. Don't bother. You will need to set up the screen modes again and again, the title screen, the intro, the main game, etc. So it would just be pointless optimization. Onto BG mode mosaic, 0 is fine. The screen bases. So by now you may have noticed two things. One, I am treating the mirror variables as words, as the STZ will write to 2107 and 2108, but then I zero BG1 and BG2. This is something I recommend. I'm not going to go into detail why now. That will probably be a thing for video 4. Short answer is to protect yourself from oops 16-bit mode and I wrote an 8-bit address and trashed something randomly. The second thing you may have noticed is the lowercase m. This is Hungarian notation. Old school machine, old school solutions. Again, video 4. The name bases, now the H and V offsets. These are doozies. They are byte double write with a hidden internal latch. So write only with internal latch. Now you must be very careful with these. If you only write once, then you will get an odd, and then all future writes will write high-low, not low-high. And you can't tell. You can't read from it to work out if you're reading high or low, and you can't read the internal latch. And there is no reset to latch to be sure. So always write to it twice. And be very careful when you're writing to them to make sure that you are 8 bits normally. In this case, I want to set both H and V to 0, so it's fine. And also be very careful when you write to 210C, because that is a byte. And if you accidentally write a word, then BG1 horizontal is going to become odd. So always modify the mirrors. And make sure you write the code to write the mirrors very carefully. And never write the registers outside of your perfect, thrice-checked code. Mode 7. If you're doing Mode 7 work, add some mirrors as well. Again, these are double write registers. Onto the windows. I have mirrors just in case. I do double writes. It's faster than switching to 8 bits, then switch back, as we need to do a special odd write up ahead and an odd number. It was just cleaner here. The object mirror, the main and sub screen designations, disable the windows, and I set the color maps to be 0 on RGB so it doesn't do anything too bad should it become active, and clear the display control too. Now onto the CPU I/O registers. We set the controller port out to FF. Most things are active low, so this is off. And we set the VBlank enable to off. A mirror for VBlank is nice. Then we just clear the rest, no need to mirror. So we have the CPU and the PPU in a known stable state. We are not done yet. We still have VRAM, CGRAM, and OAM. Why VRAM? A classic bug is accidentally enabling screen 3, but your VRAM is all 0 so you don't see anything. Then flashcard or reset leaves stuff in the VRAM and suddenly your title screen has random garbage all over it. For this, we will again DMA, a fixed value of 0. For this one, we want to write a fixed word to registers 18 and 19. We shouldn't technically need to set up the address again, but it doesn't hurt. Again, size is 0, as we want to do 64K, start at 0, and fire. Now, CGRAM. Fixed source, write a byte to address 22. We only need to do 512 bytes. Start at 0. I have to drop to 8 bits because 2122 is not safe to write to, and since 420B is a byte register, I stay 8 bits for the fire. For OAM, you don't want to set it all to 0. You want to set all sprites to be off screen and small. Since this is a common action you will want to do multiple times, and you will have an OAM mirror and you will constantly DMA OAM to VBlanks, we won't do this with custom code, but with main engine functions. This is a topic for another video. I hope you have learned something and will join me for the next video where I'll go over the weird dual address systems of SNES space and ROM space and how to fully set up and build a card image.